Hello and welcome back to Hilbert Spaces, the mathematical video course where we talk about inner products, self-adjoint operators and related stuff. And indeed, in today's part 20, we will show that the orthogonal projection operators are self-adjoint. More precisely, we will see that every idempotent self-adjoint linear operator is actually an orthogonal projection. And as always, before we go into the details, I first want to thank all the nice people who support the channel on Steady, here on YouTube or via other means. And please don't forget, as a member on Steady or Patreon, you can access a lot of additional material for the videos. For example, you find books, PDF versions and quizzes. And now without further ado, let's fix the general assumption. Let's consider a Hilbert space X. This means we have a complete inner product space, and every subspace of X is also Hilbert space if it's closed. So let's say we take a closed subspace U in X. And now we can recall from former videos that any vector X can be orthogonally projected onto the subspace U. And you also might remember the picture. If we take a vector X here, we can decompose it into two components. Both components are orthogonal to each other, and the one in U we call the orthogonal projection of X onto U. And indeed, this is the power of a Hilbert space. This orthogonal projection always uniquely exists, and we can define a linear operator. And usually we call it an orthogonal projection operator and denote it by P with index U. In fact, often one keeps it short and just says that PU is an orthogonal projection. And moreover, you can also express this operator PU by using an orthonormal basis of U. There we can use this informal notation where E alpha gives us the O and B of U. Or more correctly, we should say we can take any O and B of U, and this description of our orthogonal projection is 2. So this is really nice, but we already know much more about these orthogonal projection operators. Namely, we don't need to know anything about the subspace U or the O and B of U, because some properties for a linear operator are already enough to guarantee that we have an orthogonal projection. Namely, we only need to check two properties, and one of them is that the operator is idempotent. This means if we use P again after we have already used it once, it does not change anything anymore. So in short, P squared, which means the composition, is equal to P. And in addition to that, we also need a second property which tells us about the relation between the range of P and the kernel of P. So what we have is that the range of P is equal to the orthogonal complement of the kernel of P. And this is quite clear for an orthogonal projection, because the range of P is our closed subspace U, and the orthogonal complement of U is our kernel of P. However, what we have shown in part 16 is that these two properties are already sufficient for being an orthogonal projection, so we also have this implication here. And now the topic of today is that we can extend this equivalence even more. In fact, this is quite important, and I would say this is how you should remember an orthogonal projection as an operator. So what we have is that an orthogonal projection is equivalent to an operator which is idempotent and self-adjoint. So in short, we have P squared is equal to P and P star is equal to P. So here you see, if the adjoint of a given operator is equal to the original operator, we would say that the operator is self-adjoint. Obviously the name makes sense, and you can remember it as P star is equal to P. And clearly we can only have this property if the linear operator acts between the same Hilbert spaces left and right. So with this definition out of the way, we can go to the proof. Which means here we have to show two implications. Let's start with the easy one, where we have to show that every orthogonal projection is idempotent and self-adjoint. In fact, the first part we have already shown in part 16, so there's nothing to do there. But of course, for the self-adjointness, we have to do something. For this, we will fix two vectors x and y in X, and then we will look at the inner product. And now please don't forget the assumption, P is an operator, but it's also an orthogonal projection onto a subspace U. Indeed, it's a closed subspace in a Hilbert space, and we can use our projection theorem, which simply means that we have our unique decomposition from above for the vector x and the vector y. And of course, here the names already tell you that we have orthogonality between the corresponding components. And therefore we can finally look at the inner product y with px. And there you know, to get the adjoint of p, we have to push p to the left hand side. And indeed, this is quite easy because we can use our decomposition for x and for y. So let's start with the one for y on the left hand side. And moreover, on the right hand side, we don't have to do much because we already know by definition px is equal to the orthogonal projection of x onto u. Hence the inner product is quite simple now. We just have an addition on the left hand side and one vector on the right hand side. However, because of the orthogonality, we know that this component here will vanish in the inner product with the orthogonal projection of x onto u. Therefore, it gets even better now, because now we just have the two orthogonal projections in the inner product. And now on the other hand, let's consider the inner product py with x, which immediately tells us that we can do a similar thing as before, but now we use the decomposition for the vector x. So this is what we have on the right hand side in the inner product, and on the left hand side we just have the orthogonal projection of y onto u. And there you already see in the inner product, this vector together with that vector will vanish as well. Therefore also here, the result is this simple inner product with the two orthogonal projections inside. Hence the result is now that we have the equality of the two inner products on the left for every x and y in x. And by the uniqueness of the adjoint of an operator, we see that p star is equal to p. So this is the result, the self-adjointness is shown. So this is already something to remember, orthogonal projections are always self-adjoint operators. However, it also works the other way around. If we have the idempotency as well, then we need to have an orthogonal projection as well. So this will be the next part in our proof. And in fact, also here, we can already use what we know from part 16, namely the relation between the kernel and the range for orthogonal projections. And maybe let's first look at the range, so let's take an x from the range of p. And there we can immediately use that p is idempotent, so p squared is equal to p. And on the other hand, because x lies in the range of p, we can find a pre-image z. So simply p applied to z is equal to x. And now what we can do here is to apply p on both sides again. So we get p applied to x on the right hand side and p squared applied to z on the left hand side. However, because we are idempotent here, this square does not change anything. And therefore we also have the equality on the right hand side, so px is equal to x. So this is an important result. We don't need a different pre-image z, we can just take x as the pre-image for x if x lies in the range of p. And now in the next step what I want to do is to take the identity operator on x, which I just call I. So obviously the identity operator will not change any vector, but now I want to consider I minus p. Indeed, in the case that p is an orthogonal projection onto a closed subspace U, I minus p should be the orthogonal projection onto the orthogonal complement of U. Therefore, the two operators here should definitely be related in some sense. And we immediately see that because if we apply this operator to our vector x, then by definition we get ix minus px, which is x minus x. And this is quite interesting because it means that we map this vector to the zero vector. In other words, the vector x lies in the kernel of I minus p. So here we have shown that the range of p is a subset of this kernel. And now you might already guess that we can also show the other subset relation. This means now we choose our x from this kernel and then we show that x also lies in the range of p. And this is not so complicated because the kernel already tells us that we send this vector to the zero vector. Therefore, what we simply get here is x minus px is equal to 0. And this tells us that Px is equal to x. So this is the same equality as before, and we see that x has a pre-image and therefore x lies in the range of P. And with that we have our result. The two subspaces here are exactly the same. And the only thing we needed here was the fact that P is idempotent. And moreover, please note that a kernel of a linear operator is always a closed subspace. So we get an additional piece of information here, namely that the range of P is also a closed subspace. And this is really helpful if we want to use the double orthogonal complement. This means if you use the orthogonal complement of the orthogonal complement, then you get the original space back if we have a closed subspace. So you see, this is what we can use here for the range of P. Moreover, here inside the parentheses, we can use a property for the adjoint of an operator. Namely, the orthogonal complement of the range can be substituted by the kernel of the adjoint. So please check the last video if you don't remember this. And now finally you see at this point we can use the self-adjointness of P. So in the end what we have here is that the range of P is the orthogonal complement of the kernel of P. And there we already know this is sufficient for P being an orthogonal projection. So in conclusion, the whole proof of the equivalence is done. So now you know the set of the idempotent self-adjoint operators is exactly equal to the set of the orthogonal projections. So this fact is already very helpful, but soon you can see how we can use it even more. But first, in the next videos, I want to talk about some other important operators. So let's meet in the next video again, and I wish you a nice day. Bye bye.